Best thing to do is go get the POH. Here's the hint. You're given a KB, so you know this is a weak base. And then the last step, we want the pH, but there's a KB. Hey, there you go. Just use the KW and you'll get there. We've got this logarithmic pH scale. And then when we were talking about bases, we can look at the hydroxide concentration relative to POH. And then, of course, remember that the two add up to 14 and the two concentrations multiply together to give you the KW for water, 10 to the minus 14th. All right, let's look at a couple examples. The first one, we have calcium hydroxide. So you need to decide strong or weak. That is one of your strong bases that you have memorized. So go ahead and write the dissociation reaction. It will completely dissociate into the calcium ion, and then we get two hydroxides, okay, that are aqueous. So whenever you get a base or an acid problem, go ahead and write the reaction. It will help you. All right, so what is the pH? Well, all of that 0.1 molar calcium hydroxide is going to dissociate, and so this concentration will be, well, the hydroxide concentration will be twice that because we get two hydroxides off of each one. So that's going to be 0.2 molar. And so what is the pH? Well, the best thing to do is go get the POH. The negative log of that is going to give us, let me get my notes here, that's going to be a 0.70. Okay, so those two sig figs there are going to end up after the decimal. And then the pH is going to be 14 minus the POH, which will give us 13.30. Okay, and then you're going to ask yourself, does that make sense? Well, I've got a pretty concentrated, strong base solution, so I would expect a very high pH, and that's exactly what I have. So I like to just go ahead and get the POH, and then getting the pH is quite simple. Now, what about a weak base? Okay, you may not even recognize this as a weak base, but I'll tell you what, here's the hint. You're given a KB, so you know this is a weak base. So first step is go ahead and write this reaction. And you know, some of these bases just get really kind of hairy. So I'm going to do this. Base plus water liquid is going to be BH plus hydroxide, and this is aqueous. All right, so anytime you're feeling lazy and you don't want to write that big formula out for an acid or a base, you can just use this little format. So the KB expression is going to be the BH plus times the hydroxide divided by the base. Okay, so there is our formula. Now, we know that we have, originally we've got 0.1 molar of this, and then I'm going to say that X of it is going to come off, and so I'll get X of this and X of this. So that is our molarity across the board. So we're using that X. I chose X to be the concentration of the hydroxide. So you can even write that out if you want. X equals the hydroxide concentration. Okay, so let's go ahead and put our X's in for our substitute, right? And then as we found out in many of these basic acid equations, whenever you have a really small KB, that is basically insignificant, okay? And so that's going to make your math a whole lot easier. We're going to set this equal to the KB, which was given, 1.7 10 to the minus 9th. And then this will make the math a lot easier. We don't need to use the quadratic formula. The X is going to be equal to 1.3 10 to the negative 5 molar. And what was that? Well, that was my hydroxide concentration. Okay, so what I'll do first is get the POH. That's the negative log of that value, and that will be 4.88. And then the last step, we want the pH, so 14 minus that is going to be 9.12. And then you ask yourself, is that reasonable? I have a fairly concentrated weak base, so yes, 9 is reasonable for a weak base. All right, that's a lot. I know that is. One other thing I want to show you is the relationship between a Ka and a Kb. Now, mathematically, you can probably figure out where this comes from. Sometimes you're given an acid constant, but you need the Kb for the base related to it. So all you do is relate that to the Kw for water. So for example, let's say that I know the Kb for ammonia. I've looked that up. But I want the Ka for the conjugate for the acid, right? Related. Well, all I have to do is say the Ka for this is equal to Kw divided by the Kb. And so Kw for water is 10 to the minus 14th divided by the Kb, 1.8 10 to the minus 5th. And we will get a Ka for this acid, and it is related there. So sometimes if you don't have a Ka, you're looking for a table, but there's a Kb, hey, there you go. Just use the Kw and you'll get there.